What a pleasure to welcome you online to our small company, and thank you for listening to my presentation. This presentation will be about measurements and testing of pistons and caps of our floating cap principle. I'm standing here in our lab where we are testing a 45cc pump. It's a floating cap pump and it's actually running now. I hope you can hear it running in the background. In conventional axial piston pumps and motors, the cylinders are drilled into the central barrel or cylinder block. And here I have such a block. As you can see, these cylinders can't move. They are, so to say, the passive part of the design. The active part belongs to the pistons, and these pistons need a certain number of degrees of freedom. For instance, these slippers which are running on a swash plate. Without these degrees of freedom, the pump would not be able to work. In our floating cap principle, we have reversed this design. Now, the pistons have become the passive part. They can't move. They are locked onto the rotor. On the other hand, we have the cylinders, which are now separated from the barrel, and they can move. We call these cylinders caps. Each of these caps is translating and tumbling on a ball-shaped piston crown. Now, if you have a ball in the cylinder, it means that you have a line contact between the two components, which means that you need to have a very precise manufacturing of these two components in order to avoid excessive leakage. Aside from reducing the leakage, the floating cap principle also eliminates the problem of high friction losses between the pistons and the caps. We build a special test bench to measure the friction and the leakage of caps and pistons like these, while the piston is moving on top of or inside the caps. Now, this works for small piston diameters. In the past years, we have built many prototypes to test and prove the high efficiency of floating cap pumps and motors. However, does the principle also work if the pump or motor needs to be larger, much larger than this small unit? Let's say 100 times larger. So not 45cc, but 5000cc per revolution. Will the pistons and caps also have low friction, low wear, and low leakage if they are not this size, but this size? Furthermore, is it anyhow possible to manufacture these relatively large components from very hard material with a micrometer precision? These questions were asked by Hydratrans, a company developing transmissions for large offshore wind turbines. We also had a close cooperation with a company called VDL ETG, which did a marvelous job in manufacturing 11 pistons and caps with a high precision. But before showing you the test results, I want to show you the test bench on which these large caps and pistons have been tested. In this test bench, two pistons and caps are measured at the same time. At a maximum pressure of 350 bar, the piston force is 120 kilonewton, but the friction force is expected to be smaller than 100 newton, which is far less than the piston force, less than 1/1000th of this force. Now, how to cancel this big force, how to eliminate it? We did it by positioning two sets in a mirrored construction. And by this we were able to cancel the main hydrostatic forces of the piston and caps. One of these sets is the reference set, which is designed and measured to have no friction or no measurable friction at all. A linear actuator is moving the pistons inside the caps, and the caps are positioned in the middle and are held by a yoke which is connected to a force transducer. And this allows us to measure the friction during the entire stroke while the piston is moving inside the caps. It also allows us to measure the leakage during this movement. Here you see the piston and cap test bench during one of the first test runs, moving at a frequency of around 1 Hz. During the measurements, the cycle frequency was much lower, and this graph shows, as a function of time, the movement of the piston up and down inside the cap. As you can see, the frequency is much below 1 Hz. There was a reason why we decided to test at such a low frequency. Lifetime and durability are crucial for wind turbine applications. And we therefore decided to test the pistons and caps at the worst possible tribological conditions, which is at low piston velocity when there are no or almost no hydrodynamic effects to create an oil film. For this reason, the frequency was reduced to around 0.1 Hz during the tests. As I have mentioned in the introduction, we received 11 pistons and caps, all having slightly different piston and cylinder diameters. And this allowed us to create several different piston and cap combinations with different tolerance ranges. The tolerance difference, or the difference in diameter, varied between -7 micrometer for the most tight combination to +8 micrometer for the combination with the largest clearance fit. Of all the combinations we measured, this set with the highest fit had the best performance. As you can see, the piston has a diameter which is 7 micrometer larger than of the cap cylinder. In this presentation, I will only show you the results of this combination. Now, before coming to the results, you have to understand that the caps and pistons deform when being pressurized. The deformation is strongly dependent on the shape and the dimensions of both the cap and the piston crown. In addition, the deformation is also dependent on the position of the piston inside the cap. Now, the trick is to control the deformation in such a way that at the sealing line, the radial deformation of the piston crown is always identical to the radial deformation of the cap. And this needs to be true for all piston positions, as is shown here in this FEM analysis at various piston positions. Now to the test results. First, the measured friction. Here you see the measured friction force while the piston is moving back and forth between the two outer positions, the top and bottom dead center, the TDC and BDC. At a pressure of 50 bar, the friction force starts in the bottom dead center position at a value of around 70 Newton. From here on, the friction force reduces almost to 0 Newton during the first right half of the stroke. And after that, it stays very low until the end of the stroke. The same happens during the return stroke, only now the friction force has a negative value due to the opposite definition or direction of the piston movement. As soon as the pressure increases, the initial friction force in the bottom dead center or BDC reduces. For pressures of 250 bar and higher, the friction force becomes lower than 10 Newton during the entire stroke. Even when the pressure is increased to 350 bar, the friction force is generally below 10 Newton. And please remember that at this pressure, the piston force is 120,000 Newton. We also measured the volumetric loss in the gap between the piston and the cap. At 50 bar, the leakage is close to 0. At 150 bar, the leakage is somewhat higher, but is still very low. However, the leakage turns out to be strongly pressure dependent, and these are the results for 250 bar and 350 bar. Of course, the results which I showed to you were only the friction and leakage for just one single piston and cap. But what are the effects on the entire wind turbine transmission, which has many more pistons and caps? This is a drawing of the main wind turbine transmission as proposed by Hydratrans. The transmission uses pumps and motors with a displacement of about 5 liters per revolution. Each motor is connected to 4 pumps, which means that the motors are running 4 times as fast as the pumps. The pumps have a rated speed of 375 rpm, the motors of 1500 rpm. The rated pump pressure is 270 bar. This is the pressure at which the system will be running for most of the time. The transmission is designed also for a peak pressure of 350 bar. The rated flow is more than 7,000 liters per minute. With these data, we can calculate the effect of the friction and leakage losses of the pistons and caps on the entire transmission. The friction losses are highest at low operating pressures, but even then the friction loss is very low. At the rated pressure level, the friction losses of both the pumps and motors are close to zero. The volumetric losses are somewhat higher. At the rated pressure, the total piston cap leakage amounts to a volumetric loss of 0.5% for the pumps and a little bit more than 0.1% for the motors. We wanted to know if the volumetric losses could be reduced. Our FEM analysis showed that the sealing between the pistons and the caps could be improved by a small change of the piston design. This drawing shows where we made the change in the design. The small design change resulted in a significant reduction of the leakage by almost 50% at the higher pressure levels. The new design made the piston crown more flexible, which also resulted in a reduction of 60% of the friction losses at low operating pressures. At the rated pressure, the new design had almost no influence. With these final test results, we again calculated the effects on the entire wind turbine transmission, and this table summarizes the overall results. The measurements have proven that it is possible to reduce the overall losses of the pistons and caps to below 0.4%. This is the total loss for all pistons and caps, combined together for all pumps and motors in the transmission. Of course, there are more losses in the hydrostatic transmission, such as flow losses and bearing losses, and other friction and volumetric losses. But the piston friction and leakage losses are a significant, if not dominant, portion of the total losses in conventional piston pumps and motors. And this is where the floating cap principle brings a change. It strongly reduces the piston leakage and the friction, even when the pump or motor has a displacement of 5 liters. So here we are back in our lab. As you can hear, the pump is still running in the background. Now, what did we learn from our projects, from our experiments? First of all, we learned that it is possible to manufacture these relatively large components with a micrometer precision from harder material. We also learned that it's possible to machine these components in such a way that we can control the dimensions and the deformation, thereby reducing the volumetric losses to below 0.3%. The most interesting result is, however, that there's a very low friction even when the piston is 7 micrometers larger in diameter than the cylinder itself. The friction losses are truly negligible. And where there's no friction, there's no wear. I thank you for your attention.